Hello, everyone, and thank you for joining me on this session. Chako here, and I'm excited to share with you a few insights from research we conducted at CyberArk Labs. Please feel free to ask questions in the Q&A chat. I'll be happy to answer them. And before we start, I hope that you have a glass of water by your side. And if so, have you ever wondered how the water even got there? I mean, we're used to open the tap and get a strong flow of water. Miraculously, water just passes through pumps and pipes until it comes out at our taps and into our glasses. And of course, as long as it works, we are not interested in plumbing, as long as water reaches from one end to another. This phenomenon is not different in technology. There's a known programmer's saying, if it works, don't touch it. Well, in Kubernetes, as long as this magic works, as long as the data passes from one pod to another, why would it interest us? Let me tell you why. Because where you have less interest in the darkest spots of technology, this is where hackers will find their way in. And this is where the next attack will come from. I can't emphasize that enough. It's important for you to know exactly what happens in your Kubernetes networks. We are all used to the traditional structure of networks. We know that there's routers, switches, and firewall, all of separate components, all of them in their boxes, but in that case, they all sit under the same roof. We all want our Kubernetes clusters to be as secure as they can be. To do so, in this session, we'll dive into Kubernetes networks architecture, so you could better understand potential attack vectors. I'll demonstrate 3 of them, which include also a CVE and a new security issue in a BGP RFC. So this way, you'll know better what you're up against, so you could keep your assets safe. The best way to do this is to get into the head of the attacker, know how he thinks, understand what steps will be taken. Before my role as a team leader of a security research team, I was a team leader of a red team. My job was to be that sophisticated hacker. And after researching the field of network in Kubernetes, I can tell you one thing. You must change your current perception you have about networks and understand that the threat model is different now. Let's start. There are 3 main building blocks for Kubernetes networks. First, we have the network namespaces. Then we have the network devices, such as virtual Ethernet, bridges, and overlay devices. We also have data flow decisions. It includes IP tables, ARP tables, and so on. Let's have a look at what it looks like. We're looking at then an abstraction of a network in a worker node with 3 pods. In that case, you can see that each pod have its own network namespace, and that they are all connected to the same BR0 bridge device. Now, you might ask yourself, how can one network namespace, let's say the namespace of pod 1, can connect to the root network namespace where the bridge is at? So the answer is that we use virtual Ethernet devices, which can connect between 2 different network namespaces. Other than that, there's the overlay network device, which we'll cover more later on, and there's the ENS33 interface, which is the main interface of the worker node. We are left with the data flow decisions, the routing tables and ARP tables, and so on, that are configured by the kernel or by the network plugin pod. Now, we have one last player on the field, which is the kubeproxy here on the left side of the diagram. kubeproxy is not part of network plugin components. It's a Kubernetes component that is responsible mainly for configuring the IP tables rules according to services on the cluster. Let's say that you run a microservice with 3 different pods called my app. Each of these pods have its own IP address, and it's not a good practice to make the client remember all of these IP addresses. So what we do instead is configure one IP address for the whole service. So let's say the IP of the service will be 10.0.0.1. Now, when the client wants to reach this service, he'll just approach 10.0.0.1, and the IP tables will translate this IP address to the IP address of one of those pods. It will do a bit of load balancing on the way. So that was the last important building block of Kubernetes networking. Now that we speak the same language, we can continue and talk about the first kind of network plugins, which is layer 2 network plugins. In this chapter, we'll discuss attack vectors that utilize layer 2 network plugins features, specifically attack scenarios based on network devices and overlay networks features. We'll demonstrate these scenarios against a popular network plugin called Flannel. Layer 2 network plugins are those who sets all of the pods that are on the same node in the same subnet. More than that, they will be on the same broadcast domain. That means that all of the pods on the same node can send each other layer 2 frames, and specifically, they can send ARP packets to each other. That type of architecture increases the likelihood of man-in-the-middle attacks based on ARP spoofing attacks. An attack in which an attacker injects his MAC address instead of another MAC address. This can help an attacker to gain a man-in-the-middle position. Now, a known man-in-the-middle position, a known attack based on man-in-the-middle position is DNS spoofing. DNS spoofing is when a legitimate DNS session marked as number 1, a DNS request is sent to the DNS server. The DNS server then replies with the IP address of the requested domain name, and then the client accesses the site. In a DNS spoofing attack, an attacker in a man-in-the-middle position will capture the victim's DNS request and will send a fake DNS reply to the victim. Now the victim will then access the fake and malicious IP address instead of the legitimate IP address of the site. Let's see how it might work on Kubernetes cluster. First of all, starting with the ARP spoofing attack. An attacker on pod 1 will send the forged ARP reply to both BR0 and pod 2. That will put him in a man-in-the-middle position between BR0 and pod 2. In that case, we would expect that the DNS request would go directly to pod 1, like that. Instead, we see that the DNS request moves towards the host interface out to the DNS service. Why is that? Well, do you remember we talked about Kubernetes services and IP tables rules? Once the packet was sent from pod 2 and passed through the BR0 interface, it walked into the root network namespace, where we have IP table rules that change the destination IP. In that case, the DNS request will just follow through the IP tables and go forward to the DNS pod. But don't lose hope. When the DNS replies come back, the bridge device thinks that pod 1 is pod 2. So the packet goes to the attacker on pod 1. Then the attacker can change the content of the DNS reply and send it back to pod 2. On this case, we should consider the IP tables rules again, in that case as well. When the forged reply goes back to the root network namespace, the DNet rule will anticipate the IP address of the DNS pod, so it could translate it back to the IP address of the DNS service. Otherwise, the attack won't work. On my GitHub, you can find the Kubernetes DNS spoofing script that demonstrates this attack vector. Let's have a look at how it's done. Okay, so on the left, we have the master node, and on the right, we have an FTP pod, which is part of the FTP service. The FTP service is using TCP port 8080, and on this FTP service, there's a file with the content FTP server. Now, let's see. Okay, we open up the server. And on the top of the screen right now, you can see that we have the attacker-controlled pod, and on the bottom, we have app1 pod. If we try to download from the FTP service the test file on the app1 pod, we can see that the content of the file includes the FTP server text, which means that we download it really from the FTP service. Now we will start the DNS spoofing attack. First of all, we need to know exactly what are the IP addresses of app1 and BR0. In order to do so, we can look at the ARP table because we are on the same broadcast domain and get the IPs from there. We should also know what is the IP of the pod we are currently on, which is 10.244.144. And one last thing, you can see that the test file here is with the text attacker control pod, just so we know that. Now we start the server on the same TCP port, 8080. And we can start the attack by using the DNS spoofing script. On the target, we entered the IP address of app1. The gateway is BR0. The domain name we want to spoof is FTP, and we entered our IP address as the spoofed IP address. Now, when app1 will try to download this file, instead of reaching to the legitimate FTP, he will reach to our attacker control pod. And as you can see, the text said attacker control pod with a small smiley. So, yay. You might ask yourselves, that's cool and all, but what can I do to mitigate this risk? That's a great question. So let's talk about it for a second. There are two straightforward ways to mitigate this risk. The first one would be using a firewall, in our case, IP tables. That will include an allow list policy in which app1 can only communicate with the IP of the real FTP service. A much stronger one would be to drop the network capability from pod 1's configuration. You can do so by adding these lines you can see here to the YAML file of your pods. If there's no specific need for a packet manipulation or usage of ping messages, there's no reason for a pod to obtain the default network capability. Dropping this capability will block any attempt of the attacker to manipulate the MAC and IP headers of packets, so the attacker won't be able to perform the ARP spoofing attack in the first place. These are two pretty strong techniques, but it sounds promising, right? But wait, there's more. If you thought that these tricks will make it impossible for an attacker to spoof his IP address, you're wrong. There's another ingredient in the dish. We haven't talked about it yet, and this is the overlay network. An overlay network is an encapsulation technique in which the communication between pods in the cluster is encapsulated, and from outside of the node, it looks like node 1 is speaking with node 2. Instead, what really happens is that pod A from node 1 sends a packet to pod B on node 2. What happens is that the packet from pod A will go through the bridge device and then to the overlay device, where it will be wrapped. So let's say it will be wrapped with VXLAN headers in the overlay network device, and it will continue to the node's interface, where the original packet is the payload of the new encapsulated packet between the nodes. When the packet reaches the second node, the overlay device there will unwrap the packet and will pass the original packet without VXLAN headers to pod B. This is what an encapsulated VXLAN packet from pod A to pod B looks like. In the IP headers, we can see the IP address of the nodes. Then there's the VXLAN headers and UDP port 8472, which symbol that this is a VXLAN connection. Then there's the MAC addresses of the overlay network device. And then as the payload, we can see the IP addresses of pod A and pod B. If you'd like to see how VXLAN packets move within your Kubernetes clusters, you can use the Lua script I wrote for Wireshark. It's on my GitHub as well. Just a reminder, we talked about dropping the network capability from the attacker's pod, so the attacker won't be able to manipulate MAC and IP addresses. This should have blocked the attacker's effort to spoof any other pod. Now, we talked about the original packet being the payload of the encapsulated packet, right? So from the attacker's perspective, he can't change the layer 2 or layer 3 headers, but he can manipulate the packet. Looking at the structure of the VXLAN packet, an attacker can build a crafted payload that looks like a VXLAN inner packet and open a UDP connection with the second node on UDP port 8472. That way, the remote overlay device will think that it got an encapsulated packet. The remote device will unwrap the packet, and the inner packet, which is the attacker-controlled payload, will be treated as a legitimate packet between pods. In that case, as you can see in the diagram, the attacker can change the values of the source IP, pod X, and the destination IP, pod Y, and by that, the attacker can spoof his way out of the security controls we configured. Let's talk about a specific example. In that case, we configured the pod without the network capability, and we added an IP table rule that dictates that the web server, where there's a low privileged attacker, can't speak with the DB server on port 1433. So we would expect that an attacker won't be able to send any packets from the web server to the DB server. He's not supposed to be able to spoof his IP address. And there's an IP table rule that would block any attempt to communicate with the DB server. What can an attacker do in this case? As we talked, he can craft a VXLAN packet in a way that would pass those security controls. It's demo time. On the top right, we have the FTP service. On the bottom right, we have app1. And on the left, we have the attacker's control pod with network capabilities. So at the starting point from the attacker's pod, we can ping the FTP pod. Then we set an IP tables rules that block ping messages from the attacker's pod to the FTP pod. Let's see it. Now the ping won't work. Okay, here. Yet an attacker can still spoof the IP address of app1 and send ping messages to the FTP pod. We can see the FTP pod receives the ping request, and then we'll also see that the app1 pod receives the ping reply, even though it didn't initiate this session. Now let's make things more difficult. The attacker will be now on a pod without network capabilities. Let's see. And if we'll try to spoof app1 IP address, we can see that the operation of manipulating the packet is not permitted. Okay, so now let's block the attacker's pod access to port 8080 on the FTP pod. And now we'll use the technique of manipulating the VXLAN packet. We try to sniff this communication on port 8080 on the FTP pod. And to do so, we construct the payload and send it, leaving off the LAN style using a bash feature to send packets. We will send the crafted payload to the remote node on what you will see as UDP port 8472. So it will be unwrapped as a VXLAN packet on the other side. We send it to the IP address of the remote node to UDP port 8472. Okay, so now we'll send the crafted packet. And we can see that the FTP pod received the packet from the forged IP address of app1 pod. Yay! So we did it again. We demonstrated how we can bypass the two most common security controls. But now what? First of all, it's still a good practice to make sure you drop the network capability from your pods. Other than that, I would suggest to also block any attempt to send encapsulated packets from pods. That should completely mitigate this risk. Until this point, we talked about layer 2 network plugins, but there are a lot of layer 3 network plugins as well. When using layer 3 network plugin, we deal with different risks. We no longer have pods that share the same broadcast domain, so man-in-the-middle attacks are less common. Another key feature is different than the use of routing daemons. If we talked about bridge devices and ARP tables, here we'll talk more about routing tables and routing daemons. Routing daemons function as routers in the architecture and distribute routing data between the nodes of the cluster. They use known routing protocols such as BGP and OSPF. As we said, the threat landscape has changed. In Kubernetes environments, routers are an integral part of the host. They run on the host as a process. This aspect changed the rule of the game. We are used to routers as a separate box, one that is less vulnerable to common attack vectors. But now, if there's a vulnerable service on the host, the whole routing mechanism is under risk. And as a result, the data flow of the whole cluster is under risks as well. Another issue we should talk about, although it's less common, is pods that are configured with the root network namespace. If an attacker successfully compromises this kind of a pod, he will also get direct access to all of the routing decisions of the node and potentially of all of the cluster. Let's discuss a specific example over Calico's network plugin and what's the flow of the control plane and data plane in that case. In order for data to pass from app1 pod to the core DNS pod, the routing daemons of Calico should distribute routing data to each other. The routing daemons of node 1 tells the routing daemon of the master node that it wants to communicate with app1. It should send the packet to its overlay device and vice versa. Now, looking at the attack surface, we thought to ourselves, how can we obtain a man-in-the-middle position in this kind of architecture? We can't use any of the previous techniques, but what we can do is attack the routing daemons. To do so, we assume that an attacker was able to gain a grip as a low-privileged user, no high permissions needed here, on either the host or on a pod that is defined with root network namespace. In Calico's design, they use BGP as the routing protocol, and the known BGP attack is BGP hijacking. Now, BGP hijacking is when a hacker managed to hijack a BGP session and inject forged routing data. As you can see on the right, a BGP session starts with a TCP three-way handshake. And then there are all sorts of BGP messages, such as open message, keep alive messages, update messages, and so on. If an attacker hijacked the session, he can change the data on the left figure so that the next hop section will be the IP address of the server controlled by the attacker. It's a major risk, as this kind of an attack can change the data flow of the whole cluster just by achieving a low-privileged access to the host. Once an attacker gains a grip on a relevant position on the root network namespace, any packet he'll send out will be with the IP address of the node. By doing so, we can start a TCP session with the remote daemon in the name of the local daemon. Well, in that case, it sounds easy, right? The issue was that the BGP daemon was configured with graceful restart capability, which allowed the original session to hijack the session right back from the attacker, and no harm was done. We could leave it as it is, a denial of service attack, but we wanted more. We wanted to get a permanent grip of the BGP session so we could inject routing data and be in a man-in-the-middle position for the whole cluster. To do so, we discovered a new security issue in a BGP RFC that helped us to gain persistent BGP connection after we hijacked it. On the right, you can see the RFC that dictates that by using graceful restart mechanisms, a new connection will cause the current TCP session to drop. What we did was to send a notification message that stated that the remote BGP peer won't support this graceful restart capability. In this way, the next time the session starts, this mechanism won't work. It means that after the attacker starts the BGP session, the original session won't be able to reinitiate it. So after doing that, we can inject routing data that will cause the communication between pods to go through an attacker-controlled server outside of the cluster. We disclosed this attack vector to Calico project by Tegera, and they issued a fix in version 3.17. Let's demonstrate what this attack might look like. Okay, so here on the master node, we can see that there are two pods, app1 and dbpod. We can also see that when app1 pings, we'll try to do a ping. When app1 pings the dbpod, the attacker-controlled server won't receive any data. So now let's monitor the routing table on the node that app1 pod is running on. And we can see that the subnet of the dbpod is configured to go through node 2 IP address. What we want to do is to inject new routing data that will make packets from app1 to dbpod go through the attacker's machine. But before we do that, we should create an IP in IP overlay device in the attacker's machine as well, as packets will be sent in an IP in IP encapsulation way. Now, assuming there's a low privileged attacker on node 2, he can run the BGP hijacking attack with the new RFC issue and inject the new routing data. Now we look at the routing table, and we can see that the routing table now shows that the packets that are sent to the dbpod IP address should go through the IP address of the attacker's service. So sending ping from app1 to the dbpod will end up in the attacker's machine. Let's see. Okay, so third time the charm. That was our last demo for this presentation. And that's cool and all, but why is it important for us to talk and learn more about these attack vectors? First of all, we all must start changing our worldview from traditional networks to networks in containerized environments. The attack surface has changed, and there are a lot more new threats out there. And most importantly, you must stay with the passion that kept you here with me today in these dirty network pipelines, so that your Kubernetes clusters will be more secure and your assets will stay protected. What can you do to make it happen? Well, starting next week, you should be able to know which network plugins you use. Let's start with that. And then you should be able to identify the mechanisms that are part of your cluster networking. You should know about your network devices, the type of overlay network you use. You should know about routing components and IP address management. In the first 3 months following this presentation, you should be able to define the appropriate network policy solution for your organization. You should also must raise awareness of the risks involved in using default pod capabilities and proactively drop the use of net row capability unless it must be used. Lastly, you should configure your routing daemon to work securely by using a password for the routing protocol session. But most of all, you must not be afraid of diving into the dirt and learn how things work. Hackers do that every day. Don't let them reach you. It was a great honor and a pleasure to be here with you today. I hope you were interested and that I was able to convey the importance of the subject. We have more time for Q&A in the chat, and in addition, in a few minutes, a live Q&A session will start with me. You are welcome, and I will be happy to answer all of your questions. I am Chako from CyberArk Labs. You can find me on Twitter and read more details about the research on our blog. Thank you very much for your time.